Welcome back, everybody. This is our final week, week 16 of the 2020 kind of odd semester, huh? We're going to go through, or I'm going to go tell you what we're going to be doing. There's a really great chance that today will apply to some of you for the first part, but not all of you for the second part. And what I mean by that is I'm going to go through some announcements. I'm going to go through some ANOVA, and yes, I am putting a participation quiz for this week, so it gives you some relevance to following along with this this week. And that'll be the last participation quiz, as I mentioned last week, for the semester. And so basically, how does this apply to all of you? Well, if there's a participation quiz at the end of the week, it means that we're going to be covering information about ANOVA this week. But again, it's not going to involve any calculations. The portion of today's class that will not apply to all of you is that I'm going to be reviewing for exam number 4, the optional exam, with the last part of today's session. So I'm going to, in fact, all week have kind of that split. There will be just a little bit of review of ANOVA. What is an ANOVA? What are we doing with ANOVAs? Why are they different from t-tests? How do we distinguish them? What makes them unique? Why are they useful? And then the rest is going to be review for optional exam number 4. So again, probably not applicable to everybody, that portion of it. But nonetheless, that's the way I've set this week up. It's the best I can do for now. It makes the most sense since we're not going to be doing presentations in any formal sense like we were planning to if the semester had carried on like it was intended. But nonetheless, we are where we are, so we'll continue with this. So I'm going to move on to ANOVA. And I think in terms of announcements, the only thing I would say is that please have all of the outstanding assignments. I'm talking about the extra credit. I'm talking about the presentations by the end of the week. So I guess you have some time to work on that too if you're not reviewing for the final exams. And even if you are, hopefully you get some time to do that if that's what you intend to finish. Okay, we'll move on to ANOVA and go from there. Okay, we're back now, and at the end of week 15, we were talking about ANOVAs, when they're appropriate, what they are, how they compare with t-tests, and the differences between t-tests and ANOVA. So we're going to go ahead and take a look at another example. I finished last week with an example about testing conditions and anxiety. So we had 3 groups. The groups were high, medium, and low levels of anxiety, and whether or not these had an impact on testing scores. I think you recall that. So today we're going to be looking at a different example of ANOVA, but it's still ANOVA. And here is a simple example of an ANOVA analysis number 2. And we move on to what we see. A pair of researchers wanted to examine the scores of students in special education classes with their grade and outside of their grade. Okay, here's the null hypothesis. The null hypothesis right here is there is no difference in the means among the samples of students taking special education classes in or out of their grade levels. Okay, so we have, you can see right there, a null hypothesis talking about no difference and means. So again, that's something that is the same as a t-test. Remember, with t-test, we use the language no difference, and we're talking about means with t-tests. It's the same thing here with ANOVAs. However, let's take a look at the next bullet point. This study compared the means of averages of scores taken for those 3 groups. Here we go, 3 groups of students in the categories of reading comprehension, reading vocabulary, and math computation. So, sure, we do have the same language as t-test for the null hypothesis, okay? No differences. Okay, and means. However, take a look at this again. We're not comparing 2, we're comparing 3 groups. Okay, that would necessitate an ANOVA rather than a t-test. And I think you might recall why. If you're using multiple t-tests, you're running the risk of getting a higher than acceptable p-value. Remember, if you're running multiple t-tests, you could potentially get up into the, who knows how high. In increments of 5% p-value. Remember that? Okay, I showed you a little bit of an example of that last class. I think you'll recall. Okay, so we went ahead and well, what I did with this slide is I gave you on the last bullet item the means that were calculated. So I don't really have a slide right now showing you how the means were calculated, but you can just imagine those columns like that are always used. I use these columns all the time. Okay, we did that with the previous example of the test anxiety, but take a look here. The following F rations, or should be F ratios. I don't know why I put that there. Forget there's an N there. I'm going to cross that out. Were found for each of these categories. Reading comprehension, 3.03. Reading and vocabulary, 2.44. And math computations, 4.86. Okay, those were the F ratios. These weren't just the averages, okay? So then these were after they were generated. Okay, remember how we have the MS within, the MS between. That's what gives us the ratio, okay? Here's what we found here. Now we got it right, F ratio. Each of the calculated F scores were compared with corresponding critical values for the following following results. Okay, so reading comprehension with a F ratio of 3.03 found the null hypothesis to be true. So again, the null hypothesis to be true less than 0.05% of the time. So that would be under 5% or 0.05. What would we do then if the null hypothesis is true less than 0.05% of the time? Let me pause. What would we do? You got it. Reject it. That's right. Now look at the reading vocabulary. Found the null hypothesis to be true between 0.05 and 0.10% of the time. So that would be greater than 0.05. So what would we do with this null hypothesis? That's right. Accept it. Okay. Take a look at math computation. Found the null hypothesis to be true less than 0.01% of the time. Wow. So that made a big difference. If we found the null hypothesis to be true less than 0.01% of the time, that's clearly less than 0.05. If that's the case, we would, let me pause. That's right, reject it, okay? Did you like that? Okay. So again, to recap, when we're talking about null hypothesis, the things that we say are true, okay? We say that they are used much like t-tests, except that they're used when there are more than two categories, okay? We are comparing the means by looking at the mean square between over the mean square within. That gives us the F ratio or F score or F value, whatever you want to call it, okay? In this case, I said F ratio. Doesn't matter what you call it as long as you know what it is, okay? We are talking about ANOVAs being a stable equation where, again, we can go back to using the p-value of 0.05 because we're not using multiple t-tests. That's what makes the ANOVA so valuable, okay? So somewhere between last week's material and this week's material, hopefully you have a little bit of a better idea of what a ANOVA is. So for the next two classes this week, I'm going to start the lesson off with a review of ANOVA just to get it all ironed down so that when you participate in the participation quiz, you'll do well, okay? So I'm going to go ahead and move on to review for exam number 4, optional exam number 4. So it's going to look a little bit review-ish around here, and that's fine. If you want to review, great. If you don't need to, you can study ANOVAs and work on your extra credit or presentation or whatever else you need to do. This is not a strenuous week. It's a week where we're kind of reviewing and then also just covering a little bit of ANOVA material just because I think it's important, and it's something that you can probably use for your Social Work 111 class and beyond when you go to the master's program. Okay, if you're back with me now, there's a really great chance that what you're doing is you're reviewing or you're wanting to review for optional exam number 4, which again is used to replace a score you weren't happy with earlier in the semester. I took the best of 3, 3 out of 4 scores if you take the 4th one. So again, wanted to let you know with respect to exam number 4 that it is comprehensive insofar as it can include things from earlier in the semester, but I would say that the majority of the questions have to do with the middle and later of the semester, although it is good to kind of go over these one more time. So beginning with week 1, when we began with the basics of statistics, the main things we covered were, okay, if I can get this thing to work, Bloom's taxonomy, okay, descriptive versus inferential statistics, and the research cycle. Now, when it comes to Bloom's taxonomy, I'm not going to be asking you any questions about that on the exam number 4. However, descriptive versus inferential statistics, I usually will have questions about that, and maybe a question or two about the research cycle. So again, it's good to know those. Okay. Descriptive versus inferential statistics should be the most heavily tested category. Okay, let's take a look at that. If you remember descriptive statistics, they went like this. Okay, we started with graphs and charts. Okay, so these are all the categories of descriptive statistics. Okay, frequency distributions, measures of central tendency, measures of variability. Okay, so those were the 4 basic descriptive statistic categories. And we'll go into those just a little more in depth, and then we'll move on to inferential. Now here's a couple of examples of individual categories under descriptive, which again, this is available on Canvas under modules. So this is a PowerPoint you could use anytime. It's not anything that is exclusive to this video. You could use it anytime. Now, let me move on to graphs and charts. You remember that pie graphs or pie grams, pie charts, whatever you want to call them, okay, are the most versatile form of graphs and charts that we look at. And here's an example right here, okay? And we have others as well, but nonetheless, this was the one I used as an example in the first week of class. Okay, then we move on to frequency distributions. I think you'll recall that with frequency distributions, we have categories of variables, actually attributes of variables. So the variable here would be ages, and the attributes would be all of these categories. Okay, then we have frequencies, because this is a frequency distribution, and then we have cumulative. Okay, we have cumulative frequencies. So remember the bucket or the elevator moving down. Okay, 3. Okay, and we'd add the next one down to be 5. Okay, add the next one down to be 11. This particular graph shows this very well. Okay, the cumulative would be adding all the way down to the total number we have. And then we have the frequencies. Remember how we have the frequencies here? Okay, percentage of frequencies. And then we could have a third category, which would be cumulative frequency, which again, just like frequencies, as we move down, we're adding from the category. So again, just as when we went from 3, from here 3, we collected the 2, now we have 5, 5 collected the 6, now we have 11, 11 collected the 7, we have 18, okay. Up here we would do the same thing. We would say start with 10, okay, add the next one down, which would bring us to 10 plus 16.67 would be 26.67, okay. Collecting the next one down would be in the, 60 would be around 62, actually more than that. I'm sorry, not 62, sorry about that. It would be 52, sorry about that. So on and so forth, all the way down to 100% for cumulative frequencies. Measures of central tendency. I think you remember these pretty well. Mean, median, and mode. Okay. Again, when we're talking about specifically normal distributions eventually, which we'll do with inferential statistics, we have the mean, the median, and the mode. And we have, okay, again, the mean is going to sit in the middle, but nonetheless, the mean, as you know, is when we add up all the values of a category and divide it by the number of values that there are. Okay. That was how we did that. Okay. Measures of variability, also called dispersion. Okay, remember how we found the standard deviation? I'm not going to give you a problem on the final that deals with measures of variability or dispersion. I'm not going to, that would take way too much time to do that question plus all the others. So no, don't worry about that. But you do need to know what it is. Standard deviation would be an example of a measure of variability. Range would be another. Okay, variance. Basically, variance is just standard deviation without the square root, okay, that type of thing. So again, these are all examples of measures of variability that we covered in this class. So then we're going to move on to the next one. Well, we're going to move on to inferential statistics here momentarily, okay, but that is what we want to cover. Those are the 4 areas that you need to remember, because I could ask you a couple questions about those, even though I'm not going to cover them in giant depth that we did earlier. They're not going to be required, for example, to do a lot of problems in that way. Just recognize them, spot them on questions, specifically true or false or multiple choice. After we learned about descriptive statistics in the first week of class, we started to study inferential statistics, just the categories of what they are. And for reference and for recall is better even still. Okay, inferential statistics were these. Okay, these are what we covered. Normal distributions. Chi-square is an inferential statistic. Okay, t-tests. Okay, correlations. Pearson's R. Simple linear regression, which you really can't do without a correlation, and ANOVA. So these were the categories we talked about. You need to know these as inferential statistics. This is what we looked at and studied. And again, these are, if I was to ask you in any kind of a exam question whether something is or is not an inferential statistics, the idea is that you'll know the answer. So if I asked you a question that said correlations true or false are inferential statistics, or if I asked it the opposite, true or false correlations are descriptive statistics, you would know to say false. So again, bottom line is that's how I typically test these. As you know, I've asked these quite a bit. I've asked that type of question quite a bit during the semester. So again, we'll take a little bit more of an in-depth look at the inferential statistics now. Okay, and now we're back with inferential statistics to go a little more in depth. Okay, we look at inferential statistics, which was the second variety of statistics we looked at after descriptive. Inferential statistics are largely based on this notion that what we're doing is taking a sample from a population and making inferences, hence the term inferential, about the population based on the sample, because there's no way in the world that anyone has the resources to be able to interview absolutely without a doubt every single member of a population. So again, that's what the magic or the value of inferential statistics really is. Okay, then we went into the different kinds. So for example, normal distributions, and we spent weeks on z-scores, and we spent the same amount of weeks on method 1 versus method 2, which I'll cover at a later point during this week. But nonetheless, getting your head around the fact that normal distributions are in fact inferential because we're making inferences from the mean out to the standard deviations. Okay, and you remember this is again something that would definitely be covered on an exam. The different intervals, 68.26, 95.44. Okay, and again, you remember all of these. Okay, from the time we spent with them. Okay, you remember looking at these 99.74%. Okay, between the two, or I'm sorry, the -3 and the +3 standard deviations. But again, I'll go over that at a later time. In addition, we have inferential statistic chi-square. Okay, again, we have two nominal levels of variables. And again, I'll go over the noir in a minute. But again, chi-square is in fact an inferential statistic. That's the take-home here. You don't want to forget that. Okay. T-test. Okay, we did that. Trying to figure out whether or not the means are different. Okay. From two groups. Could be the population in the sample. It could be the samples of two distinct and unrelated groups, or it could be two samples from the same group at maybe a different time or with a different method. Okay. Correlations, I think you remember these. Okay. We're asking about whether or not the values of a data set are going this way, okay, which would be negative, or ascending, which would be positive. Okay. And we have the y and the x axes. Okay. That's another one. Regression is when we figure out, okay, line between these, and even if it's an imaginary, and where we could plug in any x to find any y, okay, and a regression line, okay. And we concluded this semester, and in fact we're on that right now, talking about ANOVAs. Okay, we're talking about, okay, usually more than two averages, okay, between groups, among groups, I should say. And you like the cartoon here. Okay, yeah, again, ANOVA is like t-test, only it is asking it's asking with respect to three instead of two groups, three or more, in fact, usually. So that's the way to kind of keep that in mind. So okay, those were the main categories. Again, on any kind of an exam situation, I'm going to be asking you to be able to distinguish between descriptive and inferential statistics. That's just basic knowledge in this class. So the only other thing to cover from the first chapter that we covered in week 1 was, in addition to inferential versus descriptive statistics, we talked about the research cycle. And the research cycle, which is defined in your book, I'll go ahead and give the parts here. I don't cover it heavily, but I might ask you a couple questions about that. Research cycle included these. Okay, number one, I can get that. Problem identification when we're deciding what it is that we're intending to study, how we want to see determine what it is that we want to know about the specific phenomenon or a group or a behavior. Okay. Next, operationalization. That's the big word that a lot of people get tripped up on. Again, this is where we're determining what we want to measure and how we want to measure it. That's one of the fundamental aspects of research that people spend a lot of time trying to get kind of honed in terms of what they want their research to look like. And once we've kind of figured out how we operationalize our variables, what we want to study, and how we want to measure it, move on to the methodology, which is how we kind of put it all together in terms of collecting the data, putting it all together in a coherent sense, making it so it fits all together, and so we can give intelligible results to be analyzed. And how do we analyze the results? Well, if we're doing something quantitatively, we're going to likely do it with statistical analysis, which is the final part that our book covers in the research cycle. So again, these are the four, and again, this shouldn't be too foreign to you. This is something that's already occurring in, I believe, Chapter 2, even though Chapter 2 is something I covered in the first week of class. Okay, problem identification, actually might be Chapter 1. I'll just verify that for you really quickly. That's in Chapter 1, I'm sorry. But the research cycle is mentioned, and in fact, it's mentioned on page 4 through, I think, 5 or 6. Nonetheless, problem identification, operationalization, methodology, and statistical analysis. Okay, in retracing this semester, week 2, we started an examination of the types of variables that we're going to look at throughout the semester. And again, as I mentioned during that week, I said this is going to follow us to the end, and sure enough, it did. The types of variables that are used for any study affect often what kind of statistical analysis you're even going to use. If you recall, later in the semester, different kinds of levels of measurement would fit with different kinds of statistical analysis. You couldn't use certain kinds. For example, you weren't going to use interval ratio with chi-square. Likewise, you weren't going to use exclusively nominal variables with correlations. So again, this is why this all mattered. But nonetheless, in week 2, here's what we started out with. We took a look at the types of variables beginning with values versus value categories. Now remember, values are the specific numbers of things. Like if I asked, how many steps did I take during the day? Okay, the answer to that question, how many steps did you take during the day, is in fact a value. It's a value. That's one way that we count variables is through the values. In fact, that's a very prominent way of doing it. Value categories would be like we're tabulating, for example, how many people identify as smokers versus non-smokers. Those can be tabulated. They're not necessarily values as much as we're getting frequencies of categories. So value categories versus values is the first thing we looked at, and we'll go over that a little bit more in a minute. But nonetheless, take a look at what else we did. Discrete versus continuous variables. Remember, discrete are the variables that we will be able to count on one hand. Okay, we don't go with 0.5. These are not variables that contain decimals. Okay, these are variables that it wouldn't make any sense to say half. So on, for example, I say, how many pets do you own? You wouldn't say 2.5. That's just strange. How many kids do you have? 3.5. No. Those would be discrete variables if you can only answer it as a whole number. Okay, continuous. If I asked somebody how many pounds of walnuts did they buy at Sprouts Market, they might say 1.5, and that makes perfect sense because we count pounds typically in halves as well, or quarters, or thirds, anything in between the whole numbers. So when we're talking about discrete, we're only going to probably be giving whole numbers because it's all that makes sense. With continuous, we're going to be using all the amounts that are in between the whole numbers as well. Okay. And finally, levels of measurement, or NOIR is my acronym I've been using. These are the ones that I spend a lot of time talking through during week 2, because these are the ones that we're going to be using the most throughout the semester. So again, these were the main topics we covered in week 2, types of variables. We'll give another little look at that now, and then move forward into the preceding weeks. So before I start, I wanted to remind you that this PowerPoint and every other one I'm using during this presentation today are available on the modules for the corresponding week. So naturally, you will find this one in week 2, since this is the one that That's the week I'm on right now. So these are always something that are available for you to use as resources. So moving on, we did a presentation, and it's still, of course, on the module for week 2. Here it is. Okay, we take a look now, at this will be the terms that will be useful to know throughout the semester. Okay, I said that data is measure collected before analysis. You can see right here, and then information is what we call interpretations of data after analysis. I did talk about that at the beginning. Okay, variable, a really important definition there. Variable I have below, a non-uniform characteristic of measured observed units. Okay, sometimes they are measurable observed units, but nonetheless are measured. Okay, attribute is a variable category. So if we're talking about whether or not somebody is a pet owner, then pet owner or non-pet owner would be attributes of the variable pet owner. Okay. All right, let's take a look at the next one. Talked about frequencies, number of times an attribute occurs within a data set. Now here's where we were getting to discrete variables, variables with only finite responses. I said letter grades here. It's not the best one, but nonetheless, you don't think like A 0.5, you either get an A or you get a B. Okay, these are finite responses. Again, that's not the best one. The better one I can think of would be things like, how many cars do you own? And someone would say 2 or 1 or none, but we wouldn't say 2.5. Okay, that doesn't make any sense. Continuous variables. Okay, now this is where GPA actually makes some sense, because people can have a 2.5 or a 3.8 or a 4 point, usually not anything above a 4 point, but anyway, 1.6. Hopefully that's no one in my class, but nonetheless, okay, at least not after my class, right? Okay, so again, continuous variables with any, they include any value on a number line. Okay, let's take a look at levels of measurement. This was Noir. Okay, I think that this PowerPoint presentation is useful for us on this. Okay, and we'll start with N, which is nominal. Okay, most basic level. The big thing to remember here is that with nominal we have mutually exclusive categories. You can only be in one category at a time. Okay, notice that there may be more than 2 categories, but never fewer than 2. There has to be at least 2 categories, and here are some great examples: smoker versus non-smoker. Okay, again, we have at least 2 categories, and if you're in one category, you can't be by definition in the other. So vegetarian, carnivore. Okay, obviously if you're in one, you can't be in the other. Okay, again, these are mutually exclusive, and that's the definition. If you're in one, you can't be in the other. Okay, look here, we have 3 categories here, or 3 attributes here, I should say. Okay, the variable here would be political party, and the attributes would be Republican, Democrat, or independent. Okay, we have 3. Once you're in one, you really don't fit in the others. That's, again, the touchstone for mutually exclusive. Okay. Ordinal. Okay, like nominal, once you are in one category, you can't be in the other, and they continue to be mutually exclusive. But what makes an ordinal variable is that the categories are also, the attributes are also ranked. So again, my favorite is the Olympics. Okay. Bronze, silver, and gold medals. If you're in one, you can't be in the other. That makes them mutually exclusive, and they're ranked so that gold is better than silver, and silver is better than bronze, and gold is better than all 3. Okay. Satisfaction surveys. Remember these: very satisfied, satisfied, neutral, dissatisfied, very dissatisfied. Okay. These are an example of ordinals. Okay. One category is better than the other. You only fit in one at a time. That's the only way you can answer. Okay, and that's another way to remember the O of ordinal. Interval. Okay, remember this one. These are ordered and mutually exclusive, so just kind of like ordinal, except that they have exact spacing between one measured unit and another. So whereas it's awfully hard to tell exactly what the difference between in the previous example, dissatisfied, right? Let me go here. Dissatisfied and very dissatisfied. Is there any way to tell specifically how you can distinguish these? No, they're kind of vague. It's just how you feel. There's no real measurement here, but that's not the case with interval. We have exact spacing. So on a thermometer, 1 degree is no further or not as far from another degree. So they're equally spaced, they're in equal units. And then the other thing, and this is the biggest part, is the interval level of measurement has no absolute zero. Okay, there's no absolute zero. So zero is just another measurement in an interval, and that's the key to that. Okay. Finally, ratio. Okay, ratio is all of the above. It is a mutually exclusive ranked with equal spacing, but then it also has an absolute zero. So we look at speedometers, weight scales, Geiger counters. Okay, again, these all have categories where if you're at one value, you can't be at another value. That makes them mutually exclusive. They are ranked because there's usually some hierarchy where one is worth more than the other. And then also we have exact spacing, and there is an absolute zero value. Okay. So to sum this up, I gave a little chart here, which is helpful. Helpful, hopefully, is what I mean to say. Okay, and again, you can see that nominal includes 2 or more measured units. Okay, measured units are ordered. Okay, and you can see that ratio includes all of these categories together. So ratio is the most complex. Ratio is the most sophisticated of them. Okay. And again, this is something you can review a couple more times. I do tend to hit noir for the final exam because it's something we spend a lot of time on, and it involves everything throughout the semester. So for week 3, we got into both graphs and frequency distributions. We're going to start with graphs today to just review the concepts. Bar graphs, what can we say about them? They're pretty simple. Let's take a look at some examples. We have nicest fruit. Now, there's a couple things I want you to notice about this particular contrast of graphs. They can be done in a way where we have vertical bars, or they can be horizontal. Doesn't really matter. Look at this. We have apples, oranges, bananas, kiwi, blueberry, and grapes. Okay, same thing over here, except that they're done this way. Now, you can see the number of people who prefer these. Doesn't change between this one and this one. It's something that you can do with bar graphs. But the most important thing to remember here about a bar graph is, look at this. The bars don't touch, and we're using only nominal levels of measurement. So if you want to take a look at what we mean by that, okay, if you found the nicest fruit to be an apple, you naturally couldn't say orange, banana, kiwi, blueberry, or grape. Okay. And because we're using nominal level of measurement, and because the bars don't touch, this must be a bar graph. Okay, let's take a look again. Here's another one. Okay, favorite type of movie. Okay, same thing here. We have specific categories and the percentage or the number or frequency of people who like them. And we have a nominal level of measurement because if you're in one, you can't be in the other. And finally, they don't touch. These must be bar graphs. Okay. You can see the same type of activity going on here with birthday of students by the month. It's the same thing. These are all examples so far of bar graphs. Okay, pie graphs or pie charts. These are very flexible. They accommodate all of the levels of measurement. The nominal, interval, ordinal, and ratio. These are all the types of levels of measurement that can be accommodated by a pie graph or pie charts. Okay. Both percentages and frequencies can be taken into account. Okay, you can notice that here 2 or 7.1% of the students received a D, 4 or 14.3% received an A. So again, we can accommodate both frequencies and percentages with pie graphs or pie charts. Okay. Same thing with pet ownership, which is a chart I like. Okay. Take a look at histograms by contrast. What do you notice that's different between a bar graph and a histogram? Well, for one thing, okay, what's going on here? The bars do touch. This is a histogram. Okay, the other thing is that we're measuring not at the nominal level. These aren't just categories. These are actually values. These are values that you can measure typically against each other. Okay, and they're all pertaining to the same topic. Okay. So again, this is not nominal level of measurement, and the bars don't touch. I'm sorry, the bars do touch. This has got to be a histogram. Okay, same thing here. Okay, we have another one here. Okay, notice these are all measured in years that are equal amounts, and then also percentages right here are not just categories. Okay, like for example, frequency of categories of people who like action movies versus comedy movies, so on and so forth. Okay. Frequency polygons, okay, look an awful lot like histograms, only they have the middle point. Okay, look at the middle point here with a dot. Now we're beginning to see lines connecting the dots among these categories. It's starting to look a little bit like a normal distribution, isn't it? That's the point. Okay. Roll of 2 dice. Okay, that looks definitely like a normal distribution, and it should because they are normally distributed. Okay, but that's an example of a histogram, okay, in action. So absolutely what we're seeing here is something you're going to need to remember. Okay.